All right, so you're in 7.2. The theme, I think, in today's class was recognizing that there's two different ways you can identify, well, one way to find the equilibrium or equilibria, if there's more than one, of a differential equation, and two ways you can classify the equilibrias as either stable or unstable. So let's do an example of that. We'll talk about both ways, and then I've got some example problems from the book we can run through here and hopefully clarify a few things. So let's suppose we've got a population of squirrels that's growing according to this differential equation. And what I want to keep reminding you of, I don't think there's been a huge deal made of it right now in 17b, but it's just a good thing to know. We're doing the same idea right now in 17c, talking about two populations, maybe predator-prey models, stuff like that. And being familiar with what's going on, I'm going to cover this up for a second. So last time on Friday, I talked about a couple of population models. I'm going to just cover this up for a second. Number one, if I said that's how the squirrels were growing, according to that, without just the first term, who remembers what kind of growth would that describe? If it was just dn dt equals 2n. And one way to think about that is that saying the change, remember dn dt is the rate of change. The change in the population each unit of time is double the population size, right? That's 2n. N is the population size, and this is the change in the population each unit of time is double. That would describe, if you had a population of squirrels where, let's say each month, let's say t was in months, each month the population was double the previous population, what kind of population growth would that be? Yeah, that would end up being exponential growth. And I know that's confusing because this has the equation of a line, right? That's like y equals 2x. But that's something a little bit different. This would describe exponential growth. Now, the other thing we talked about on Friday was if we throw in this term, you may remember that this is describing logistics growth, the idea of population growing with a certain maximum population, sustainable population, which would be 1,000 in this case. That's logistics growth. And then we throw on this third term, which we're going to figure out what that actually does to our model. So let's start. Let's find our equilibria first. Equilibria is when there's, so let me just emphasize this. This is again is the growth rate of our population. So if we're looking for equilibria, that would imply no change, which means no growth, no change or growth, right? So it always to find your equilibria, you're just going to set dn dt equal to 0. Whoops, why did I put 500 there? I don't know what I was combining those two. This is 1,000. N minus 50. And it's kind of already set up for us. It's in factored form. So what population sizes would make this whole thing equal to 0? One of them would be 0. It's pretty easy to see that if n was 1,000, 1,000 over 1,000 would be 1. 1 minus 1 would be 0. And then also from this factor, 50. And these are equilibria populations. You've seen the notation is like n hat in this case, or y hat if you're using y, whatever variable. And then to classify the equilibria as either stable or unstable, one technique is using a phase plot. Okay, and this is the one where you're graphing the function. And I know there were a lot of, I can tell from the questions this morning, just the previous hour, that there was a lot of confusion on what's happening with this. To do this, what we are literally doing is graphing our differential equation our differential equation, let me rewrite it since I can't see it. It was 2n 1 minus n over 1,000 times n minus 50. We're graphing this as if it was like y equals 2x times 1 minus x over 1,000 times x minus 50, as if it was just a regular yx graph where, but the difference, of course, is what's acting like n, or what's acting like x is n. So your x-axis is n, and remember that n is the actual population size, right? That is how many squirrels I have at some moment in time. And dn dt is not the population size, as we said, that's the growth rate. Okay, but we'll talk about those in a second. For now, just think about how you would graph something like y equals 2x 1 minus x over 1,000 times x minus 50. And knowing that actually up here, because one of the techniques for graphing something like this is to find your x-intercepts. And remember, to find your x-intercepts, you would be setting your equation equal to 0, which we've already done. We know that this y would be 0 when x is 0, 1,000, or 50. So those are your x-intercepts. I guess 50 comes first. And then recognizing, I guess, you should have a little bit of graphing experience. If you were to multiply this all out, how many people see this graph as being a cubic polynomial, right? Your biggest power of x would be x to the third if you were to multiply that all out. And we know that cubic polynomials, or you should know, they always, like, if these are the x-intercepts, cubic polynomials are either going to look like this. They're going to go, let's say I start at 0, they're going to go up through here and then up like that. That's one possibility. Or they might go down like this. It's going to either be this. I wish I could, I can't erase in pen, but I can do it kind of lightly. It's either going to be this or the opposite, right? Might do this. That's how cubic graphs look, right? So how do I figure out which is which? Well, all I really need to do is pick a test number. You could pick it anywhere you want. But let's just say, for example, I pick a test number. Let's say I pick 2,000. Now, I'm not going to draw this to scale, but let's say I pick 2,000. That would, to scale, it would be further. If I plug 2,000 in for x, all I really need to know is whether my function is up here when x is 2,000 or down here. In other words, whether it's positive or negative. So if I put in 2,000 for x, this term will be positive. 1 minus, if x is 2, that's why I chose 2,000, because 2,000 over 1,000 is just 2. 1 minus 2 would be negative, and 2,000 minus 50 would be positive. So a positive times a positive means this whole thing will come out negative if n or x was 2,000. And so what that tells me is I know when n is 2,000, my graph is down here. And that's really all I need to know, because it's going to go through these intercepts. You know, and likewise, you could pick any number. It didn't have to be 2,000. If I picked, like, you know, say I pick something in between 50 and 1,000, like let's say I picked 500, I could plug in 500 and see that that's positive. 500 over 1,000 would be a half. 1 minus a half is positive, and 500 minus, they would all be positive, and so I know my graph would be up here, right? So one way or the other, plug in a number to kind of figure out what your graph looks like. And then here's the idea. me explain it one more time. I think there was a lot of confusion in class because what I think people were thinking was that that this is a graph of the squirrel population. This isn't a graph of the squirrel population. This is a graph of the growth rate, right? It's not, this itself is not the graph of the squirrel population. What is the squirrel population? It's actually the x-axis, huh? This is the actual size of the squirrel population. But I can infer a lot of stuff here. And so you already kind of went through this in class, but there's two basic things, right? Whenever dn dt or dy dt is greater than 0, what does that mean? That means n is increasing, just like in 17a. When f prime of x was positive, that means f of x was increasing. So where is dn dt? dn dt is like y. Where is it positive? It's positive anywhere you're up here, right? This is where dn dt is greater than 0. Anything up here and below is where dn dt is negative. So dn dt is positive, certainly anywhere here, right? Anywhere here, dn dt is positive. And I think what threw people off is when they said n was increasing, you're like, wait, it's going down right here. Remember that we're not talking about, this is not the graph of n, this is the graph of dn dt. It is definitely positive throughout this whole region here. Now, what is n? N is the x-axis. And so what that means is the reason we do this is if n is increasing in this thing, and this is n, and you can see 50, 1,000, 2,000, getting bigger means going this way. So we draw our arrows going to the right. That's how we denote that n is increasing, because n is the x-axis, and it's getting bigger for all these values. Also, notice also over here, in this portion of the graph, dn dt is above the x-axis. So you would have arrows going here. I guess this was 0. And so then likewise, dn dt, whenever it's less than 0, that means n is decreasing. And so that would be here, right? It's dn dt is negative here. It's below the x-axis. So that means for any population size from 1,000 onward, my population would be decreasing. Arrows going to the left, n's getting smaller. Same thing in here. dn dt is negative in here too. So n decreasing. So my arrows here would go to the left. Okay, so then hopefully you got the idea how to read these arrows, but let's just review it again. So here's the idea. Maybe I'll start from the right side. If my population of squirrels were to ever jump to 2,000, what this is telling me is my population would steadily decrease until it gets to 1,000. Because that's an equilibrium. Remember, there's no change there. That's going to stay the same. Let me also re-emphasize that. The whole idea of an equilibrium population is that if my population of squirrels reaches 1,000, it will stay there forever, according to this model. Of course, that's not realistic in life, but this will always stay at 1,000. Same thing with 50. So if my population were to jump bigger than 1,000, like let's say a bunch of squirrels were introduced to the arboretum, then what we would expect is the squirrel population would steadily decline until it gets to 1,000. Likewise, let's assume my squirrel population suddenly dipped below 1,000. Let's say it went to like 500 here or something like that. Maybe there was a disease or something that affected the squirrels, and then the disease was over or something. Then the squirrel population would steadily increase until it gets to 1,000. So if we move either way, if the squirrel population dips below or just bigger than 1,000, it comes back. And that's a characteristic of what kind of stability, stable or unstable. That is stable. Exactly. This is stable. Whereas 50, that's an equilibrium. So if the squirrel population magically hit 50, it would in theory stay at 50 forever. But what this is saying is if my squirrel population, even if I get one extra squirrel, 51 squirrels, according to this model, would be enough to push the population. Eventually, it would go to this equilibrium. So it moves away from the 50. And if my squirrel population were, if I were to lose one squirrel and have 49 squirrels, unfortunately, what that means is my squirrel population would decline to 0. So in this case, either way I move from 50, it goes away from my equilibrium. So this equilibrium is unstable. Exactly. And then the 0, I mean, it doesn't make sense to have negative squirrels, but if I suppose if you did, notice it comes back either way. When the arrows point inward, that is stable. So there, maybe you could do that. When you see the arrows going together, that's stable. Unstable is when the arrows are pointing away from each other. Okay, we'll talk about the other method in a second here. But something you should be expected to do as well is, and maybe this will add some better meaning to what this whole picture is saying, is to sketch actual solution curves for our population of squirrels for various initial population sizes. So what I'm going to do here is not, this isn't the same graph. Now I'm graphing n. This is the population size as a function of time. According to this model, you should be able to take this graph and translate it to what I'm going to do here. So here's how you do this. We know that 50 was an equilibrium. When the population of squirrels was 50, that would, again, that what that says is your population in theory would just stay at 50. It would be a horizontal line. Same thing for 1,000. These are my equilibriums. And I suppose 0 as well, right? But that's like a no-brainer, huh? If you have 0 squirrels, you'll always have 0 squirrels. So, but what we might be interested in if we're studying the squirrel population is what would happen to our squirrel population if our initial squirrel population was 40 squirrels. So let's just put that, I'm going to use a different color, but so let's say I was to start at 40. Well, we can tell from this picture here that when our squirrel population is below 50, it's going to decline to 0. It's going to go down to 0. So what I would expect over time for my squirrel population is it's going to steadily decline. And the way this works, it's kind of like asymptotically, so it'll get closer and closer to 0 as time goes on. If my initial population of squirrels was 100, we can use our phase plot to see that what would happen if I started at 100, which is somewhere in here, it would steadily increase until it gets to my equilibrium of 1,000. And the way it does is it's kind of like the logistics growth that I showed you before. It would actually first start increasing and then it would tail off as it gets closer. It doesn't actually hit there, but it would get closer and closer to 1,000. If I started at 900, which is really close to the carrying capacity, at that point, it's no longer, it's just going to be really just leveling off. And then if my squirrel population were to suddenly jump to 1,200, we saw that over here, it's going to, because 1,000's a stable equilibrium, the population will actually decline gradually. So these are actually just solution curves. That's different than a phase plot. When you're asked to graph a phase plot, that's when you're graphing the derivative, the dndt thing. And I think this was, I kind of left the meeting right at the very end, but I think this is what that last example, at least the one I saw, was referring to, is this idea, which to me makes sense. It makes sense to me that there's a carrying capacity, right? That they're based on competition for resources, whatever, that there's probably some theoretical limit for the squirrel population. But it also makes sense to me, what we're seeing here is there's also a minimum population size. Because what this is saying is if my squirrel population doesn't hit 50, at least 50, it's going to die out. And you could kind of imagine why that's true. Yeah, if it was 49, it would fall. Only time and population would fall back to if the population is at 49, anything below here. Of course, if you only had 2 squirrels, think about the whole arboretum, the chances that those 2 squirrels meet each other and make other squirrels is pretty slim, right? So your population is going to decline to 0, right? But what this is saying is 50 is your minimum population size. Otherwise, you just don't have enough squirrels to sustain a population, right? So that idea is called the Ali effect. Is the idea of a minimum population size. Is required to prevent the extinction of a population. I don't know that, I mean, I guess that's more of a biology term. That's not a math thing, but just to acknowledge that, which to me adds a sense of more realisticness to it, right? It's another step above just a regular logistics model, is knowing that there's also incorporating some minimum population. Okay. Now, another way, which you did talk about, to determine the stability is with the derivative. And this is what you talked about in class as well. So let me, I'll tell you what, I'll just use the same graph. My graph that I just graphed looks something like this. And the idea of this method is that no matter what your graph looks like, you can have all kinds of wiggles on your graph and everything. If your graph crosses an equilibrium with a negative slope, with a slope that's negative, what's going to happen if it's crossing with a negative slope? That means this must have been positive here, which means your arrows must have gone this way, and this is below the x-axis. It must have gone this way. You're always going to have a stable equilibrium, right? If it crosses, same thing over here, huh? If it crosses with a negative slope, the arrows would go this way and go this way. This would be stable as well. So if it's a negative slope, it's going to correspond to a stable equilibrium. And then the opposite, if your graph crosses an equilibrium with a positive slope, you can see that the arrows would actually go away because it's positive here, negative there. And so that would correspond to unstable. I think a reason a lot of folks are confused about this is, how do I find the slope of this graph? Of course, that means I need to take the derivative. But what am I taking the derivative of? I'm taking the derivative of our equation, which is already a derivative, right? Remember, this equation equaled, for the one we just did, I need to take the derivative of this equation, but it's already a derivative, right? And so that looks kind of weird. And so what we do is, this is where we call it, you saw we call that either, she had g of y, I'll switch it to that in a second. In my case, I guess it would be g of n, right? Just because it looks weird to take the derivative of a derivative, we'll just call it g of n, and then we'll just take the derivative of that instead. Does that make sense? And so this is just acknowledging what we just found. If the slope of the graph is positive at n hat, then n hat is unstable. If the slope is negative at one of your equilibriums, then it is stable. And that leads to, let's see if I can fit this in here, what's called the local stability criterion. Yeah, so here, so like I was saying, it's because it's already a derivative that you'd be taking the derivative, we just call it g of y in this case. If it's, and so we take the derivative of it, plug in our equilibrium, and if it's positive, if it's greater than 0, then your equilibrium is unstable. And if it's negative, hey, you know what? I like that. I don't want you to lose points for this. She was acknowledging that when it's stable, we should actually refer to it as locally stable. I'll try to remember to do that too. And that is called the local stability criterion. And it's especially useful. You can imagine, what if I'm sure you're already thinking that, what if I can't graph that? That last one we did was a cubic graph. I mean, they certainly get worse than that. So what if our differential equation is not so easy to graph? Well, at least we have this to fall back on, right? I actually like the graphing method if it's possible to graph, because to me, it's so visual and you can see what's happening. This, you kind of lose a little bit of the feeling of what's going on when we do this technique, but it works. So, and it doesn't require us graphing. I know you already have this in your notes, so I was just going to get to the first example here. Okay, so this, I'm choosing some problems from the book here. So this is number 8. And they say, find and classify the stability of the equilibria for this equation. dy dt equals 5y times 2e to the negative y minus 1. See, if I had to graph this, this would be hard. This would not be easy to graph. So we're going to definitely be using this technique to classify the equilibrium, but we have to find them first. So first step is to find the equilibria by setting this equal to 0. And it's already multiplied out. So one equilibrium is going to come from 5y equaling 0, which happens when y is 0. The other one's going to come from setting this equal to 0. Which requires a little work here, doesn't it? So if I isolate the e to the negative y, I would add 1 divided by 2. So e to the negative y is 1/2. To get at least the negative y by itself, I would take the ln of both sides. That's just negative y. So my second equilibrium is negative ln of 1/2. It's fine if you leave it like this. I'm thinking like things in the back of the book. They love to simplify things. You might also see this written like this. Actually, let's do this. Remember your rules of logs? One of your rules of logs is that's like a -1. And remember how it can float up to the exponent? So you could write this as positive ln of 1/2 to the -1. And what's 1/2 to the -1? When you take a fraction to a negative power, you're just flipping it. So that would be ln of 2. So I don't think it really matters. You could leave it like this, or you could, I think this looks better, but you know, if you didn't think of doing that, this should be fine as well. All right, so now, since we're not going to graph this thing, we need to figure out whether each of these equilibria are stable or unstable. So we'll call we'll call this, like I said, we're going to call that g of y, 5y 2e to the negative y minus 1. And what we need to do is take the derivative. And unfortunately, what we have, this is a product, isn't it? These are two different functions. So we're going to need to do the product rule. F prime g plus f g prime. Derivative of 5y is 5 times g 2e to the negative y minus 1 plus f, which is 5y. And the derivative of 2e to the negative y is 2e to the negative y times the derivative of negative y, which is negative 1. If it's okay, I'm going to put that in front. And of course, the derivative of negative 1 is 0. Rather than putting the negative 1 here, I'll just put it to the front. And then the idea is once you have your derivative, you're going to then one by one plug in your two equilibrium. Let's start with y hat being 0. That was one of your equilibrias. Yeah. So that's going to give me 5 times 2e to the 0 minus 1 plus 5 times 0. That's good. So I can just skip the rest, but this is whole going to be 0 because of that 0. E to the 0 is 1. So this is really just 2 minus 1 times 5. I end up getting positive 5. Don't have to worry about the number itself, but the fact that this is greater than 0 tells me what? That tells me that my equilibrium is unstable. Exactly. That tells me that if I were whatever that crazy graph looks like, I don't know what it looks like. It's passing through with a positive slope. So my arrows would go away. So this is unstable. And then we have to plug in. Well, see, now I have a choice. You know what? I actually think it's better. Okay, here, you know how I was saying like the second equilibrium, you could either have it as negative ln of 1/2. That's how it kind of naturally comes out, or you could rewrite it like this. Let's think about what we're going to do. We're going to plug this back in right here. And I think I'd rather have the negative here so that the two negatives cancel out. I think I'd rather use this. So I'm going to use this one. You could use either one, but so let's do g prime gives me 5 times negative ln of 1/2 times 2e to the negative ln of 1/2 minus 1. That's here. And then I still have 5 plus 5. Oh, wait. This, I did it wrong, didn't I? This didn't need to go there, did it? I should have just had 5 times 2e, there we go, minus 1. I didn't need that, but this one's going to need it, plus 5 negative ln of 1/2 times negative 2e to the negative ln of 1/2. Oh my goodness. All right, let's see what happens. Well, 2e to the negative ln of 1/2 is just 2e to the ln of 1/2 minus 1 plus 5 negative ln 1/2 times negative 2e. This is going to cancel and just make that ln of 1/2. Using your inverse property, what is e to the ln of 1/2? Remember, this is just, that's just 1/2. And if you think about it, that's just 1 minus 1 now. That's going to make this whole thing 0 right there. Let's take these two negatives. Let's take these two negatives and make it positive. 5 ln 1/2. And then I'm going to have times 2. And just like we did before, that's just 1/2. And 2 times 1/2 is just 1. So this part just cancels out. So this is a little bit tricky because what I end up with is 5 ln of 1/2. All right, this is where you're okay. Because how many people agree that looks positive? That looks like a positive number. But some of you in here, I've had all the way since fall quarter, we were taking pre-calc together. And I remember, because we talk about in pre-calc, and some of you took pre-calc as well, and you discussed the graph of natural log of x. And I remember telling my pre-calc class in the fall that you're going to need it, and you got to know it precisely, not just generally what it looks like. Remember that the ln graph, it's the inverse of your e graph. And your e graph, which is a little more well-known, passes through 0, 1. Your ln graph is you reflect that around the line y equals x. So it passes through 1, 0. Because what I want you to know is, can you tell me what the ln of 1/2 is? What kind of a number it is? 1/2 is right here. If I plug that into my ln function, the ln of 1/2 I can see is going to be a negative number, isn't it? It's less than 0. This right here is negative. So that makes the whole thing negative. Less than 0. Therefore, my equilibrium of negative ln of 1/2 is stable. That's kind of tricky, isn't it? Yeah. Questions? Okay. That was number 8 from 7.2. Let's try number 9. Slightly different question. Whoops. They still want us to find the equilibria of these equations, but they've left something unknown. They've left a constant a there. So our equilibrium is going to be in terms of a. And then they want us to figure out what value of a we have to have so that our equilibrium is stable. Stable. So what we want is, right, we want g prime of y hat, whatever our equilibrium is, we want this to be less than 0. We want it to be negative. Okay, let's start by finding our equilibrium. Remember, y prime is just another way to write dy dt. And so to find your equilibria, you're just setting this equal to 0. And that's going to give me, if I solve for y, that'll be y hat because it's a special equilibrium. Move the 1 over, divide by a. Negative 1 over a is my equilibrium. And now to find out what value makes this, what value of a makes this a stable equilibrium, perhaps you can see it right there, but we want to take g prime of y. And remember, for this step, we're just calling this g of y, and we're just taking the derivative of that. What's g prime of y? If a is a constant. Yeah, it's just going to be a, isn't it? Because 1, 0, and then a times y is just going to be a. Now, this is just a constant. So like if I evaluate this here, this is my derivative for all values of y, right? I'm going to put for all values of y, including this one, right? So what's the requirement for this to be stable? So we need, so a must be less than 0 for y hat equaling negative 1 over a to be stable. This is the answer, really, right there. There were like 3 parts to this. There's a B and a C. So why don't you try B? Find your equilibria first. It'll be in terms of, I think there's only one. It'll be in terms of A. And then see if you can take the derivative of that and figure out what A would need to be to make it negative, to make it stable. All right, so if you move this over, if you set it equal to 0, move over the e to the negative ay. You can take the ln of both sides, or you could just ask yourself this. When is e to anything ever going to equal 1? E to what's equal 1? Only when this part's equal to 0, right? Or you can follow through and take the ln of both sides. Ln of 1 equals ln of e to the negative ay. You just have to know the ln of 1 is 0. And this just becomes negative ay, which means, oh, that means y hat. If I divide 0 by negative a, that's just 0. Yeah, which is 0. Yeah. Yeah, negative ln of 1 over 0 would, over a would be basically the same thing. It would be 0. There's another thing, right, where you should know your, if you know your graph, right, you know the ln of 1 is 0 because it passes through. That's your x-intercept. Okay, so now we have to, so we're going to let g of y be 1 minus e to the negative ay, and we need to test out, see what value of a makes this stable. So the derivative, that will be 0. The derivative of negative e to the negative ay is negative e to the negative ay times, remember, a is a constant. So it's like if you had negative 2y, it would be multiplied by negative 2. So it's just negative a. And this is the same thing if I take the negatives, put them together, AE to the negative AY. And recall, we are specifically trying to find the value of A that makes this a stable equilibrium. That was the problem directions. So we want this to come out to be negative. What do we know about this part right here? E to anything. I've asked this to some of my students over the past few quarters. What do you know about E to any power? What kind of a number will you always get? I mean, think about, even if we know E to a positive power, right, that's definitely positive. But what about E to the negative 2? Isn't that just 1 over E squared, which is still positive, huh? No matter what you raise E to, even if this comes out to be a negative power, that is always positive. So the only possible way this could come out to be negative, because that's what we're looking for, is only if A is negative. So I'll put G prime of Y will be negative only if A is less than 0. And I'll just put in because E to the negative AY is always positive. All right, so there's more questions like this. There's also some application problems, but I chose these two because these seem like really, we've been talking about like short test type of questions, right? Or quiz questions can't be super long or they would not work on a short test. So these would probably be high candidates for types of questions I would expect you might see. But they do take some practice, so. There's one more part we can do that. Maybe I'll make that my warm up for Wednesday. All right, you all.